Okay. So, good morning, everybody. So last time we talked about the Michelson-Morley experiment and ether, right? Do you have any questions about this? I hope that, like, if you do, you can please unmute yourself and ask a question at any point in time. And if you're watching on YouTube, you can, excuse me, you can post your question in the chat window. By now, I think most of you have figured out how to where to get the YouTube video. It's on the channel. It's on my channel. So, but in case that's not clear, we can share the link with you. Okay, so the question is today we're going to talk about Lorentz transformations. Right. So I introduced them yesterday, and I told you that the reason we need Lorentz transformations is because of what we call empirical evidence. Okay, so what do you mean by empirical evidence? 9, right. So the empirical evidence that we have is that Maxwell's laws, right? That is the evidence that we have. Maxwell's laws, and the fact that they are not invariant on the Galilean transformation. So if you want to, so let's look at Maxwell's laws, and let's try to think of a transformation which will leave this equation invariant under a change of coordinates. Okay, so let's try to come up with something which does that. Now, to do that, first I will rewrite this expression in a slightly different way. I'll take both the terms over to one side. Okay. And I will write this expression in this way. Okay. What is the purpose of doing this? So if you look at this expression can be written as d by dx minus 1 by c d by dt d by dx plus 1 by c d by dt and e is equal to 0. Okay. Okay. No, we don't want to do. So if we look at this expression and we stare at it for a little bit, right, what we see is that this kind of a quantity is appearing. C square, T square in this combination is appearing. And if we want to switch to a different frame of reference, let's say x prime squared, then, well, we know that so this would be the Maxwell equation in the new frame of reference. And again, we have, right, in this frame of reference, c squared t prime squared minus x prime squared. So one way to ask that the Maxwell equation remains the same in both frames of reference is to insist that if you look at this expression, this operator in the two different frames, that this equality should be satisfied. This operator should have the same form when you go from the unprimed frame to the primed frame. So one way to make sure that that happens is that if this condition is obeyed, that means ct squared minus x squared in one frame of reference should be the same as ct prime squared minus x prime squared in the other frame of reference. Okay. Now, what should be the form of x and t such that this equation is satisfied? So to understand that, let's look at another equation where, let's say, we have x squared plus y squared and x prime squared plus y prime squared. Okay, so let's say we have some coordinates x, y, and we change to a different set of coordinates x prime comma y prime, and we require that x prime plus y prime squared is equal to x prime squared, right? So you will see what the similarity is in just a little bit. Now, what sort of expressions for x and y would satisfy this equality? Can anybody take a guess?
Sine and cos.
Sorry. Somebody said something, I didn't catch that. Okay, well, so one thing that would satisfy this equality is that if you have x prime is equal to x times cosine theta minus y times sine theta, and y prime is equal to x times sine theta plus y times cosine. All right. What is this? This is a rotation, right? Cosine theta minus sine theta, sine theta. So if I write it as a matrix, I can write it like this, x, y. Right? So you have one set of coordinates x, y. In this set of coordinates, if you look at any vector, any point, the radius of that vector is x squared plus y squared, right? Now, if I perform a rotation of my coordinate axis, so I change to a different set of coordinates, let's say x prime and y prime. What happens to the point R? It is labeled by a different set of coordinates now. It is labeled by x prime, y prime. But the radius, right, R prime, which is given by this x prime squared plus y prime squared, this doesn't change, right? So if you want a transformation between x and y, which preserves this expression, that transformation should take the form of this rotation. Okay. Now I can ask the same question, but with a minus sign instead. What if I have two sets of coordinates, xy and x prime, y prime, but I want a transformation between those two coordinates such that this expression with a minus sign is a constant.
Tan and secant functions.
Right. So the solution would be that instead of cosine and sine, one would use hyperbolic cosine and hyperbolic sine. So if you write down x prime y prime as some sinh theta cos theta sinh theta xy. So then you can easily check that x prime squared minus y prime squared would be equal to x square y minus y. And this comes from the fact that when you work out this algebra, right, you will get this expression cos h squared minus sin h squared, and then you would use the identity that this is 1. The same way that if you want to, when you look at x prime squared plus y prime squared, what would you get? You would get a term which involves cosine squared and sine squared, cosine squared plus sine squared. So here you would be using the identity that cosine squared plus sine squared is equal to 1, right? Now, so this expression is exactly the same as this, right? So instead of writing x and y and x prime and y prime, I can also write ct prime squared minus x prime squared and ct squared minus x, right? So what is my transformation now? Ct prime, x prime, these are my new coordinates. There is a factor of c, but that's just a constant factor, so that just shows up as a multiplicative factor. Okay? Is equal to sinh theta cos theta sinh theta times ct. Okay. And if you do this and you calculate what is this quantity, the square of this minus this, you will get that this is present. So if you have this sort of a transformation, then what will that imply? That will imply that this operator will be the same. So this operator in the new frame of reference will look exactly the same. And if that operator looks exactly the same, then Maxwell's equation will look exactly the same. And what would be the implication of that? That would mean that the speed of light, right, the speed of Maxwell's waves doesn't change as you go from one frame to another frame, right? And that is Einstein's second postulate. Okay, so we can write down finally what are, so instead of sine and cosine, I'll just exchange these and write this as ct prime. So cos theta sin theta. Okay. So finally, I have x prime is equal to x times cos theta plus ct sin theta. Ct prime is equal to x times sin theta plus ct. Okay. Now the question is, what is this theta, right? This theta we don't know yet. So, well, if you divide the left hand sides of both equations, so if you take x and divide it by ct prime, what does this give you? This gives you v prime by c, right? This gives you the velocity of the in the prime coordinates, the velocity of whatever our object is, whose coordinates are given by x prime and t prime. All right, and then you can ask, or actually instead of saying this, we can ask what happens if x prime is equal to 0. Now x prime is equal to 0 is the origin of the coordinate system in O prime, right? So this is x prime, ct prime. This is the O prime frame of reference. This is x, this is ct. This is the O frame of reference. And let's say the O prime frame is moving with respect to the O frame with some speed v naught. And if we ask, how does the origin of this coordinate system, how does that origin look as seen by an observer in O, right? So what is the origin? The origin is given by this equation, x prime is equal to 0, right? Right. So if x prime is equal to 0, that means if I look at this expression, I get x times cos theta is equal to minus ct sin theta, or x by ct is equal to minus tan h theta. And what is x by ct? So x is the location of this origin in O's frame of reference, and t is the time associated with this point in O's frame of reference. So this is what? This is the velocity of the origin of O prime divided by c.
Sir, can you repeat? Why did we take x prime 0, sir?
Okay. So instead of taking x prime equal to 0, you can look at any other. We took it just for convenience, right? So x prime is equal to 0 is a fixed point in O prime's frame of reference, right? It's the origin. We identify the origin of these coordinates as x prime is equal to 0, right? Origin is x is equal to 0.
Yes, sir.
Okay. But when I look at this origin, now you put something at the origin. Let's say you put a ball at the origin. And you ask, what is the position of this ball as seen by O? Right? So as seen by O, the position of the ball, right? So the position of the ball satisfies this equation in O prime frame of reference, right? Right? Yes or no? I mean, is it? You ask the question, so I'm just asking you, like, is this clear? Say something. Yes, no. Who asked that question? I don't know. Can you please just.
Sir, can you repeat, sir?
Ashwin, okay. So yeah, just tell me to repeat. I'll repeat. Doesn't matter. Okay.
Yes, sir.
I'm looking at the origin of I'm in O prime. All right. This is me. This is you. I put a ball at the origin of my coordinate system. Whatever my coordinate system. Okay. What is the location of my ball in my frame of reference?
X prime 0.
X prime 0.
Yes, sir.
Now X prime has to satisfy this equation, right?
Yes, sir.
So if I put in this equation, if I put X prime is equal to 0, what do I get? I get this relationship between X and T.
Yes,
What
sir.
is X and T?
Right.
X is the location of the ball as seen by you,
Yes, sir.
right? And T is the time interval.
Yes, sir.
So this tells me what is this theta parameter. It tells me that this theta parameter is related to this velocity,
Yes, sir.
the relative velocity of O prime and O.
Yes, sir.
And I'm getting a minus sign. So if, for convenience, I can just work with the velocity going in the opposite direction. Okay.
Yes.
So I'll say tan theta is equal to V naught pi, which is equal to beta. So that's what this theta is. This theta is tan inverse, and it is known as the rapidity. Is this fine? I mean, the
Yes.
reasoning. Now, in this expression, we have cos and sinh. So once we know what tan is, we can write down what cos and sinh are, right?
Yes.
What is cos theta in terms of tan theta?
We get hyperbolic, sir.
So if I look at tan h theta and I say 1 minus, let's say, tan h square theta, what do I get? I get cos square theta minus sin square theta over cos square equal to 1 by cos square, right? So that means I can write cos theta as 1 by square root of 1 minus tan h square theta.
Yes, sir.
Okay. And what is this? This is 1 by root of 1 minus V naught square by C square. This quotient is related to the relative velocity of the two frames of reference. See, when people's videos are turned on, then I can see your reactions. For example, I can see the reaction of Shashank, and he's like nodding his head. And that tells me that, I managed to convey some fact, some information to you. So if I have that feedback, then I know that I'm doing something that is correct. That's why visual communication, non-verbal communication is important. So let me write that down again. Tan h theta is equal to V naught by C. Cosine theta is equal to 1 over 1 minus tan h squared theta, which is equal to root of 1 minus V squared by C. And similarly, sin theta can be written as square root of, so cosine minus sin 1 is equal to cos square theta minus 1. And in terms of tan h theta, it would be.
Sorry, it's 1 minus cos square h square theta.
No, it will be this, because cos square minus sin square is equal to 1. So sin square is equal to cos square minus 1. Okay.
Yes.
So if I substitute this expression for cosine, what will I get? I'll get root of this thing squared, that is 1 over 1 minus V naught square by C square minus 1, which will be root of V naught square by C square over 1 minus V naught square by C square. So this becomes beta divided by root of 1 minus V naught square. Right? Now beta is the velocity in units of the speed of light, V naught by c. Okay. And this factor that we keep seeing again and again is called gamma. So this is called the Lorentz factor. So what is this cos theta? Cos theta is just equal to gamma. And sin theta is equal to beta times gamma. So finally, I can write down the expression for my coordinate transformation. What do I get? Take this, right? And what is this? X times gamma plus Ct times beta gamma. And this becomes X times beta gamma plus Ct times. Okay. And this is exactly the same as the form that I showed you. Instead of beta, if you write minus beta, so what will happen? So if you look at the first expression, x prime is equal to, first of all, gamma is common, right? Gamma is common here. So I can write this as x plus beta times c times t. What is beta times c? It's V naught, right? So this becomes gamma times x plus V naught t. Right? This is what I had told you in the previous class is the form of the Lorentz transformation. Like this. X only that here it was minus V versus plus V naught. It just depends on the sense in which you're looking at the which frame of reference are you looking at, right? And what about t prime? So t prime can be written as, now this x, I have this factor of c, I'll take that c factor over here, I'll get, so okay, so first let me write this gamma ct plus beta x, right? And then I'll divide both sides by c. So I'll get t prime is equal to gamma times t. What is beta divided by c? That is equal to V naught by c square times x. Right? So it's the same expression that I had shown you in the last class, t minus V naught by c square by x, only differences with a minus sign. So if you look at this transformation from the perspective of this is, we are going from the O coordinates to the O prime coordinates. If you go from the O to the O prime, if you go from O prime to O, what will happen? We will get the inverse Lorentz transformation. Now, here we can directly use a principle of relativity, right? That if O prime is moving in the positive x direction with V naught with respect to O, then O is moving in the negative x direction as with minus V naught with respect to O prime, right? So what is the inverse of the
Prime is equal to
gamma times x plus V naught t. T prime is equal to gamma times t plus v naught by c square x. And what will be the expression for x in terms of x prime and t prime? It will be a Lorentz transformation again, right? The only difference is that v naught will become minus v naught.
Minus V naught.
That's the only thing that changes. This is the inverse. Either one of them you can call the Lorentz transformation and the other as its inverse, right? The Lorentz transformation. So if you call LV, right, as the Lorentz transformation, then L of minus V naught is the inverse of this. That's it. Right? The transformation is the same. I mean, it doesn't, the sign is not important, right? Sometimes if you've been through, I don't know, if you have just blindly looked at a lot of problems, you might just think that, well, this is the Lorentz transformation and this is the inverse Lorentz transformation. No, they're both Lorentz transformations. Just the same way that when I talk about rotations, right? Whether I rotate this way or this way, they are both rotations, right? Whether I rotate by plus theta or minus theta, they are both rotations. It's the same thing. Yes. Niranjan, if you are having trouble in what do you call it? I can't hear what you're trying to say, so maybe you can put in the chat. If you want, you can ask a question in the chat also. Okay. Or if that doesn't work, you can just message me on Telegram. There are lots of different ways. But did you have a question, Niranjan? Okay, if you have a question, you please ask. Okay. So this is one way to derive the Lorentz transformation. There are many different ways to derive the Lorentz transformation. Okay. One other method that you will often see in textbooks is that you start from the Galilean transformation, and then you use the properties of space of translation invariance. That means space looks the same everywhere and time looks the same everywhere. And then you get some set of algebraic equations, and you solve them and you get the Lorentz transformation. That's another method. Right. This method I'm introducing because it introduces this concept. It introduces this concept. And what is this concept? Well, again, let us look at the space case. So this is I can call this the space relation, right? Both are spatial coordinates. This is the space time, right? One coordinate is spatial, other coordinate is time-like. So we say space-like and time-like. One coordinate is space-like, another coordinate is time-like. Actually, coordinates are not space-like and time-like. Intervals are, but this is just some terminology to distinguish between this and this. Right? Now, when we look at when we look at ordinary space, right, our space case, what happens when I perform a rotation? Let's say I have 2 points, x1 and y1, and x2 and y2. Now I can define the distance between these 2 points, right? What is the first? Let me define the displacement operator, right? Displacement operator delta r, not operator, just the vector displacement is what? x2 minus x1, y2 minus y1, right? I can write that as delta x comma delta y. Now I perform this rotation of my coordinates, right? So when I perform the rotation, what happens? The coordinates of my 2 points, they change, right? Then I get this delta r prime. The displacement vector between those 2 points in the new coordinates becomes x2 prime, x1 prime, y2 prime, y1 prime, I write it delta x prime comma delta y prime, right? Now as vectors, these two look different, right? This vector and this vector, they look different. But if I calculate the length, what do I get for delta r?
Both are same.
Both are same, no?
Yes, sir.
So that this means that spatial intervals, right, or more in line with the terminology I was using, space intervals are conserved, right? They don't change under rotation, right? So this is a basic property of geometry, right? Of spatial geometry. This applies in 2 dimensions, in 3 dimensions, in any number of dimensions, right? Whenever you have rotations, this will be true. Whenever you have translations also, this will still be true. You can translate your coordinates with respect to another set, right? But that will not change the relative displacement, right? The length of the relative displacement. So I think maybe you can see where I'm going with this, that now when we look at space-time, we are talking about relativity. And in relativity, time becomes a dynamic object, right? This is the one lesson that we have. That time is no longer the same in different observers' frames of reference. So when I describe an event in one frame of reference, I have to give the time coordinate as well. I can't just give the space coordinate. I have to say what is the time coordinate. So this is a point in space-time, okay? And space-time is a geometry. It has a geometry just the way that space has geometry, right? Space has geometry because you can define this length, right, using the Pythagorean theorem. So the same way you can define a geometry on space-time also. So I have 2 events now, okay? So the same way that I have 2 points here, now I have 2 sets of points here, x2 and ct2. And we refer to these points as, we call them events. Right? Event is something that happens, right? So for instance, if a light bulb flashes, right? If there's a flash of light, then I am the observer. I will say this flash of light happened at some position x and at some position time as seen by me, right? So this flash of light happened 100 meters south and at the time, let's say 10:30 a.m. in my whatever my local time is, right? Another observer might look at the same flash and say that for that person, that flash happened, at a different location, 200 meters west, and at a time I could be something else, 4 p.m. right? So now you imagine there are two such events, two such flashes. The first, so one flash is at x1 is at time position x and at time t as seen by me. And the other flash is at position x2 and time t2 as seen by me. Right? So these times can be different or they can be the same, it doesn't matter. Right? And now I go to, there is an observer who is moving with respect to me, right? So here I have a rotation, a spatial rotation. Here what do I get? I get a hyperbolic rotation, right? I get a Lorentz transformation. Which is what? Which is a hyperbolic rotation. It's a rotation in this space-time, in this space-time plane, xt plane. This is the reason why I've been drawing all my frames of reference as x and t. So what happens according to the other observers? Oh crap, you have class from 11:15. Okay, well, all right, then go to the other class. I think you can see what I'm talking about. You have x prime. I'll just take 2 more minutes. Okay, these are your new coordinates, and once again we can define a displacement vector, but now it is delta x comma delta t. Sorry, no vector, just delta x and delta t. And here I have delta r prime is delta x prime comma delta t. Right? But now how do I define the length of a vector? The length of a vector delta r is equal to delta x squared minus c squared delta t squared. And this distance is called the space-time interval. And this interval does not change regardless of the frame of reference you are in. All right, guys. So thanks for sticking around. Sorry for taking up too much of your time. I apologize to the next faculty also for keeping you here. Okay. All right. So I'll see you all next week. And wishing all of you a very happy new year, and a very safe.
Thank you, sir.
Thank you, and same to you, sir.
Thank
Thank
you.
you.
Thank you.
Thank you,
Happy New
sir.
Year, sir.
Thank you, and same to you, sir.
Thank you, sir. Happy New Year.
Thank you, sir.
If you have any questions, you can ask those questions now, or you can ask them later on Moodle or anytime.
Bye, sir.
Okay.